Alrighty, so this is lecture number 8 in the 2021 version of my computer architecture course that I'm currently offering here at GUC, along with the OS course, and they kind of go together, and both of them are definitely prerequisites for my favorite course. One of my two favorite courses that I'm giving here at GUC, and those are the embedded system course for sure, that most probably most of you are gonna be taken next year, not next week, and the cyber physical system elective that will come later in the ninth. So in the last lecture, we've seen a simple implementation of the ISA, so the microarchitecture of an ISA, which is functional, not optimal, not optimized, not high performance, but I mean it works and good for us. However, we this is our square one, and then we're gonna go ahead and build over it in order to, because you already know me by now, and if there's something that I'm obsessed about, especially in the CA and OS course and later maybe, is performance, so computer performance. So how are we going to go from that simple, um, functional, not optimized solution to a fast, um, implementation that has a better performance, right? So we've seen the data path between the different hardware components that are needed to be able to execute any kind of instruction that is defined in the ISA, and the MIPS is ISA because we're using MIPS as an example throughout this course. And we've seen that there's a way to route the different inputs and outputs, for instance, and we use a particular hardware component. I should know it by now because you've already taken it, apparently, according to the fun discussions that I had with your colleagues in the face-to-face lectures. So basically, you already know, if we wanted to select between different inputs in order to get it into a digital system, well, we can use a particular hardware component, which is the MUX. And this is how we're gonna route stuff within our data path with our implementation to make sure that all the instructions are taken into consideration. And then we've seen that we've defined 3 types of instructions, and for each type, well, there is a particular ALU operation that is relevant and that is needed. For instance, any memory operation would definitely need some kind of adder to be able to use, the base and the offset. So to add the offset to the base, so we need an add operation that will happen most probably because it's a mathematical operation. It will happen in the ALU, arithmetic units, and logical one, of course. Um, and we've defined some kind of control unit for that particular ALU. So in function of the type of instruction that we're tackling, well, we're going to go ahead and select one of the possible operations in the ALU. So that was the first control unit in the data path that we tackled at the very end of last week's lecture. And in today's online video recap, call it whatever you want to call it, even though it contains all the information that I'm spitting out in the face-to-face lectures, I personally like to call it a recap video, because at the end of the day, there's no interaction, and I said it like a zillion times. I'm gonna say it one more time. I don't see the advantage of watching a video over some interactive system. So I would definitely go for an interactive system, but we're gonna do what with the tools that are offered to us here. So bear with me, and let's all together make some efforts in order to make this work. All right. So yeah. So in this lecture, we're gonna go ahead and check out how to deal with the different control signals, right? So these were the blue things in the data path that I showed you in last week's video, and you can see it. I mean, this is an analogy which is extremely interesting here, because I don't know if any of you had internships or do know how the control happens in the train stations, but I had the opportunity to see that closely back home. And you know that you have different tracks in a train station, and of course you need to route the different wagons on the different trains to make sure that no trains are on the same path at the same time. So basically you have some kind of switches that are manually controlled, and now more and more automatically, of course, but I mean usually manual control by a human operator. And then on track A, for instance, if we're having an incoming train from this side, well, we need to make sure that no other train will be on that track coming from that side, right? So we need to do the proper switching in order for the trains to be smoothly, to run smoothly on the different tracks. And this is exactly what we need to do on the data path. We need to make sure that it's one at a time. There's some kind of exclusion between the different instructions, and one instruction might need a path that is common with another instruction. So basically, we need to know how to switch between those, and the switching happens using the MUX, for instance, in the microarchitecture. And then we're gonna get to pipelining and see what is, I'm gonna introduce pipelining for now, and then we're gonna see in more details in the next video. All right, so this is what we seen last time together in the first part of last week's video, and we've seen the different hardware components and the different data path that is in that particular schematic here. And we've noticed that for a particular hardware component, let's say the register file here, we have a common input, and then we have a choice between two different sources for that particular input, and this is why we're using a MUX. And then again, the source of that particular input will be dictated by the value of what we're applying here at the MUX level in order to choose between this input or that input. Fair enough? And this goes for every other component that is here. And we can notice that even for the hardware components themselves, so basically these are for the MUXes, we need to choose the different sources between two different sources, for instance. And for the other different hardware components that we have here, well, we need to know whether we're gonna go ahead and put something in the memory or get something from the memory. Are we going to use the register file to to put something in it, etc., etc. So what I need you to keep in mind for the very next slide is what you're looking at here. So those are the things that we're gonna go ahead and try and put values to in order to be able to control the data path to execute one instruction. Fair enough? Here you can see the ALU control unit that I covered in detail in the last video, and you can see that here we have an ALU operation. So this is the input to my ALU control, and then we're going to spit out the 4-bit output in order to be able to choose one of the operations that will happen in ALU. So for instance, if we're having something that is related to memory, we know that we need to have an addition, so we need to identify that this is a load or store, something related to the memory, and hence we're going to go ahead and select the addition. This is so easy for the memory. It's easy also for the branching. The question is, what happens if I have a NAR type instruction here? This means that I need to do something with two registers and store back the result in another register. But the operation is not systematic. It's not systematically an addition or subtraction. It will depend on something, and it could be any operation offered by the ALU. So how would I know which operation to do when I have an R type? Well, this is where another field is needed, another input is needed, and that input could be read from the instruction itself. And to be specific, well, this is the 6-bit field that is needed from the instruction, least significant bits, in order to know the functionality. It's called funct, so functionality, in order to know the operation that will happen in the ALU. Fair enough? And how many bits are needed here? So you need to remember that from last time. If we're trying to cover 3 instructions, so how many bits are needed in order to pick one out of 3 instructions? We're gonna see that in more details on the next slide. So please keep those control signals in mind, and we're gonna find out how to deal with them. That being said, so basically I'm having my control unit. The control unit will be determined by the input of the control unit will determine these outputs that are the control signals after all. And something will tell me, well, something will dictate the different values for those output signals, and that something is definitely coming from the instruction, and I'll leave it up to you to determine which field exactly will determine the different ones and zeros that should go there. I want you to notice something here though. So imagine that I do that a lot. So imagine I'm giving you something new that you've never seen before in your final exam or later on in your professional life. I'm hiring you to work on something, and I'm giving you some documentation, and I'm telling you that In the output signals here, and the output control signals that I have here, most of them have the same number of bits. All of them but one. And go ahead and try and have a feel which one has a more than one bit as as width. So here you can notice everything here, everywhere we have a thin line here, everywhere but the ALU op. And using your experience, so if you noticed from last week's video, the ALU op, this is the thing that goes into the ALU control unit, and then it will spit out the 4 bits that I needed for the ALU. However, remember, because we're going to go ahead and choose one of the 3 possible instruction types that we have, so basically here we have 2 bits, and every other output control signal here has only 1 bit, and this is why they're thin. This one is thick, and those are all thin. All right, so let's go and check the values for that particular one, and then you're gonna go ahead and trace every single, trace it yourself manually with rest eyes all alone at home. So let's do the load word. So remember, the load word will be an instruction that is dealing with some hardware units, and particularly the load and store are the only instructions that can reference the memory. So this has to do with the memory. So let's see what type of operation is needed for the memory. We've decided last week we need an addition. So basically in the table that we've seen last week, this means that the MIPS people decided to give it this code. So for the ALU op, we're gonna spit out 00. That will correspond to an addition in the ALU. Fair enough. Do we have in the mux that will let us know the register destination, which one should we choose from the inputs? Which one we're gonna choose? Well, we're gonna put it to 0, so we're gonna toggle it off, and this would be the first input of the mux. Again, reference back to the previous slide where we have the data path, and we're gonna see it on the very next slide as well, because I'm gonna include this one. All right. So the ALU source, same thingy. So basically, remember, for the ALU we have the normal one that is stemming from the register file, and then we have 2 possibilities: one that is coming from somewhere, and something that is coming from somewhere else. So the first somewhere is from the other source, register source that could be in the that is in the register file, or it could be from the direct field, the offset that is coming from the instruction. In this case, we need it from the offset because this is a load word and we have an offset, so we only have one source register here, right? So again, this is toggle on and off the mux to know which one, which path to choose as an input for the ALU later on. Are we going to write to the register file again? Yes, so we need to put one here. Are we going to get something from the memory? So it's a load word, so basically yes, we're gonna go ahead and read from the memory. Are we going to write from the memory? No, so this should be a 0, right? And the branch is not concerned by here. Is this a memory to register instruction in the sense of, are we going to get something and store it back in the register file? Well, yes. So basically this is why we have a 1 here. Fair enough? Go ahead and trace it for everyone and for every other instruction type, and we're gonna see that it all makes sense. It's logical. Now you're seeing the full, where's my pointer? The full simple implementation. I mean, you're not seeing the jump you've covered in the tutorial, so I'm not going to include it here. All you have to do is to include the jump here as well. But here now you're seeing the full simple data path hardware implementation of the ISA. So the microarchitecture, the data path, including the control. So we have a control unit that we get some information. That would get some information from a particular field from the instruction, and you should know what that field, the name of that field by now. I'm surely hoping so. And then I'm gonna spit out the different values that are needed to control the routing of a particular instruction. And you can also notice here the thicker line that is using more than 1 bit, unlike the others. Fair enough? You can pause the video a little bit and contemplate and go ahead and trace the different things that we talked about in the earlier slide. Fair enough. Now, of course, knowing me by now, I'm interested in something. So this is fully functional. It works perfectly, no problem at all. But then again, might not be satisfied with it because it might be not very optimal performance-wise. So we're gonna find a little bit more about that in the upcoming slides. Alrighty. So here, the field that we were talking about is the opcode, and we can notice that for each opcode, we'll have it as an input to the control unit, and then we're gonna spit out the different outputs that we tackled in the prior slides. All right, so go ahead and check for every one of them and make sure to trace it on the data path to fully understand how things are routed. Right. A couple of things before tackling performance. I need you to have this in mind. First off, in order to be able to tackle performance, we are interested in the cycles, so the time. Each and every time I mention performance, the only how can I put it correctly? The only reliable metric for performance is the wall clock time. It's the execution time that you're gonna time it yourself using the wall clock. You know, the universal time. Your watch using a timer, something that reflects the real time. Fair enough. The time in real life. And if you remember quite well the different components of the performance equation that I taught you. And by the way, there's the execution time as a metric, and there's another metric that is also reliable. And the other metric, you should know it by now, is fixing the amount of time that you're gonna observe. You know, the window of time that you're gonna use to observe how many jobs will your system be able to spit out, and that metric is called throughput. These are the two only things that I trust in when it comes to performance because they're reliable. All right, so in the execution time performance equation, we've seen that we have different components, and one of them is the CPI, the cycles per instruction. So basically, and one approach is go ahead and find out for each instruction that I have in my ISA, well, how many cycles are needed. This is important because using the number of cycles and finally using the frequency of the hardware clock that is implemented in my computer, I can, measure how much time will my program take in order to be able to execute. Fair enough. I'm gonna use another approach in today's lecture. I'm gonna go ahead and try to fix the cycle that is needed for some instruction that should include every other instruction. Fair enough. And then I'm gonna go ahead and determine how big the cycle should be to be able to be sure that it takes into consideration every other instruction that is present on the ISA. Right, so I'm gonna get back to that in a few moments, but for now, imagine that I wanna measure how much time for your whole class will your whole class take in order to, I don't know, race from point A to point B. So basically, if I time the slowest person that is running, right, this means that I'm guaranteeing that after this time, well, everyone, because the slowest one has taken X seconds, for instance, like after X seconds, it's a guarantee that every other competitor is already at the finish line. Fair enough. So I'm going to use this logic in my analysis today. All right. Another thing that I need you to keep in mind: the system that we're having here is edge triggered. So what does it mean to have a system that is edge triggered? I'm using a clock. So basically, after your DSD and CO courses, I'm surely hoping that you understand what that is. So something will go like that. This is your clock, and this will determine the frequency. So basically, if you have a clock, you have something, an ascending arrow here, and a descending one here, and then an ascending one here, and a descending one here. So these are what we call the edges, right? So this is a rising edge and this is a falling edge, and a rising edge all the way next to the next rising edge, this will determine my clock cycle, this one clock cycle. So when I do edge triggering, this means that if I'm going to, again, feel free to pause the video and think about it before getting the answer, because again, I don't want to spoon feed you anything at all. I need you to think as engineers, and then because I cannot get your answers, so you need to do it yourself. You need to fake it. Fair enough? So do it yourself. So at the edge here, right, I will be getting some data. So let's say I want to read the value of variable a, generally speaking, right? All I'm going to do is I'm gonna go ahead and have a sample read the actual content of variable a at the edge. And because a is a variable, this means that a could change at any time. So even if there are changing happening here, I'm not going to read the change. I'm not going to read a all the way here, but I'm going to go ahead and read it again at the edge here. So this value could be 1, even though I could have had 1 0 1 0 1 0 here. So you can see that here I feel like it's some kind of guarantee that I have a stable value whenever I'm doing that at the edges. That's one. That's advantage number 1. If it were not edge triggered, this means that I could try to read it here, and here you can see that I don't have a guarantee. It could be any value, and this is what we call in electronics usually and in hardware a race condition. Alright, and I think I mentioned it in the OS course. And for those who are not following the OS course, a race condition means that I imagine that there are two programs are trying to, this is an example that has nothing to do with that, but it's important. Let's call it variable B, Ali, to try to avoid confusion. So variable B in program 1 is having the value of 1. In program B, in program 2 is having the value of 5. And then you're gonna go ahead in parallel, in full parallelism here, you're gonna start the two programs here. What would be at the very end of the execution of the programs the value of B? Well, this will depend on something. It will depend on the slowest program to finish execution. Fair enough? Because if this program is faster, this means that it will change the value of B into 1. But then again, when the second program will reach that instruction, because it's slower than the first one, well, the value will be 5. So you can see, you can never really know if you're going full parallel, well, what should be the value. It could depend on a microsecond, nanosecond, it could depend on so many things. Exactly here. So in order to have a stable version, here you're minimizing the chances of having a non-stable version. Well, actually, there are no chances of having a non-stable version. They're extremely infinitely small. Infinitésimalement. Infinitely small. Alright, so this is one of the advantages. Edge triggered, this means that I'm not subject to race condition anymore. And there's a second advantage. Let me wipe that out and try to analyze the second objective, and at the same time you need to think about it. Future engineers, check. Voila. And let's do that here. So this is my clock again. Tuck. Rising, falling, rising. Alright, so if I'm reading here, and my reading is done here, what is the other advantage that I could have here? Well, another advantage could be, if I read here, I could write at the falling edge. See? So I can, in one cycle, even if the cycle is not done yet, I can do maybe 2 things. Hold on. So doing 2 things, this means that if I needed 2 cycles, one cycle to do the reading and 1 cycle to do the writing, this means that I can now do in 1 cycle both the reading and the writing. So I'm cutting in half the time that is needed to do a full read-write. Hence, I'm improving performance. See? Nothing but advantages. Alright, so yeah. in the data path that I'm suggesting here, we've noticed that we first have the instruction memory, and then we have a bunch of things, and then at the almost the very end we have the data memory. Here you can see it in two ways. Either they're physically separate from a microarchitectural point of view, and this means that we're not in von Neumann anymore. Fair enough. This means that I have a separate data for separate memory for data and separate data for separate memory for data and separate memory for instruction. I'm not in von Neumann. There's another type of class of architecture here. I'm gonna name it. Or it could also mean that I'm still in von Neumann with a separate memory, which is true. I'm having data and instructions. However, as we learned from the earlier videos together, that the memory has some cache to it. And data cache is separate from instruction cache. So from the data path point of view, well, this is transparent to me. All I'm seeing is memory. However, from an implementation point of view, well, I could be seeing, and this is what I'm seeing, and the actual data path is the cache, is the representation of the memory using the cache. So the first memory level that I deal with after the registers. So this is why I have the instruction cache as a representative of the instruction memory, but the data path see it as an instruction memory, and the data memory has a data cache memory, data cache as a representative for itself. Hence the two separate memories. Fair enough? It could be either way. To be honest, naturally, it's the cache thingy. So it's the cache approach that is being used here. Fair enough? But it could have been the other way. Doesn't really matter. Alright, and one last thing, we've noticed that in the data path as well, we needed an addition for, well, as an addition operation in the ALU. But then again, some other component, some other instruction type, for some other reason needed an addition operation and did not use the ALU, but it just used an adder somewhere. What was that instruction, by the way? Yep, it was a branch. So basically, any other elements that needed more than once in the data path will be duplicated. So these are the premises of my system. So back to the performance equation here of the execution time, the three components of that. And we've covered that a lot, so I'm not going to go through here. I'm interested in the CPI, and then we're gonna see something about here. So how many clock cycles per instruction, I said that I'm not going to count the clock cycles per instruction. I'm gonna go ahead and make one clock cycle. I want to impose one clock cycle for every single instruction that is out there, and I need to make sure that it's fit enough. Yeah, it's big enough to fit the all instructions that exist out there. So if I'm doing an addition, or I'm doing a memory instruction, or I'm doing an ALU, or I'm doing something else, well, all of those should take a one cycle. So I'm fixing that. So if I'm fixing that, in order to make sure that it fits, I'm fixing that one. And if I wanted to make sure that everything could happen in a clock cycle, this means that I need to adapt the length of my clock cycle. So I need to know how much time, how big, how long is my clock cycle. So this is when I need to determine now. Fair enough? I need to stretch it enough to be big enough to take into consideration any instruction that is defined in the ISA. This is our next challenge together in this video. Alright, so keep that in mind. And in order to make sure that a clock cycle would fit any instruction out there, well, we're gonna go ahead and apply what we applied to the analogy that I used earlier. Well, if I have 10 people running, if I'm tying them, I need to make sure that after that time, before that time, the time of the last one to get to the finish line, well, everyone is there. So if I copy that approach and use it here, all I need to make sure of is the clock cycle is wide enough to take into consideration the slowest instruction, the longest, the one that will take the most time. Fair enough? Yep. So the simple implementation, I'm gonna call it a single cycle implementation now because I'm fixing, it's a one cycle implementation. So from now on, I'm gonna use this terminology. And as I said, I should the same length for every instruction. So I'm gonna fix that. That's it. It will be one cycle, and the cycle should be x seconds. I'm trying to determine x. So the slowest instruction, the instruction that will be the longest in the path, will be the one that will dictate the length of my clock cycle. Now the challenge is to know which instruction is that. So which instruction will go through the longest through the different components. So yeah, go ahead and think about it, and I'm gonna put back the data path, and you're gonna go ahead and pause the video, analyze it, and then try to give an answer and compare it to the answer that I'm gonna give in a second. All right, so let's find out the longest path. Would a NAR type instruction be the longest one? Let's see. I'm gonna go through the PC instruction memory for sure. I'm gonna fetch it, get it here. I'm decoding, and I'm getting here. R type, I'm reading those registers. I'm R type, so it means that I'm gonna use the ALU. Should I need the memory? Nope, because it's an R type. And then I need to get back to my register file. Whoa, doesn't look like the longest one. What could be the longest one? Maybe a branch instruction? I'm not using memory, and I think the longest one should at least reach here. So it should take into consideration the data memory component. So it could be a store word. Let's try the store word. Store word, it will come from here to here. I'm gonna read the base from here. I'm gonna read the offset from here, add them together. Gonna go ahead and save the word. I think I'm good. This is long enough. I've taken into consideration every component here, and it's long enough. But is it really though? No, because I'm stopping here. Is there a longer one? Yes. Instead of store word, maybe a load word will get me to here, and then back to the register file. So there's an extra step. So this load word is an extra step longer than the store word. Right, so let's give some values to the time spent in each of the components, and then we're gonna go ahead and see how much time does in this case, my load word instruction take in order to execute. So load word, it will go through here, base and offset, addition, get it from here, and back to the register file. So let's do that. 150 nanoseconds here, 0 here, 1 nanoseconds, so 151. ALU, I'm gonna spend 2 nanoseconds, 153, 150 in the memory here, so 303 nanoseconds, and then back to my register files, 304. So a total of 304 nanoseconds. Fair enough? This is the longest one. I need you to notice something else here, and this is one of the typical exam questions that I keep on asking in the face-to-face lectures, but I'm going to ask it to you again and try to debate with your colleagues before trying to find out the answer. Flashback to your memory hierarchy lecture, right? This particular schema here, it put some value, something that I said when it comes to the memory hierarchy, and we've seen the pyramid, or the triangle. You can notice the answer is you can notice that I spend 1 nanosecond on the register file, so reading and writing to a register, it will only take 1 nanosecond. However, dealing with the memory, so it's this, the more you go to the memory hierarchy, the more time you'll be spending. And here you can see that I'm spending 150 nanoseconds, so it's order of magnitudes bigger than the time that you spend on the registers. So things that you store and read from the registers are way faster than the actual memory. And you can go ahead and imagine if we're dealing with the disk, for instance. So yeah, I didn't lie to you here. Fair enough. All right, so let's see. This will dictate my clock cycle. Now, what would my frequency be then? If I have a 1 clock cycle for each instruction now, all I have to do is 1 over the period, so the cycle. This will give me my frequency, which is 3 megahertz. And in today's standards, 3 megahertz is rather a slow computer. All right, fair enough. All right, so my next question is how to go faster. I surely hope that people will not tell me that we need to make the clock bigger. It wouldn't make any sense. How to go faster now? One approach is to try to go and do stuff in parallel. I mean, as much as I can. Fair enough? Can I parallelize in a way or another? Can I overlap things in a way or another? This is the big question that I'm gonna try and solve. All right, so I'm gonna give you the premise of what we call pipelining, and then we're gonna continue that in the next video. All right, so to use an analogy, so today I'm gonna use an analogy. I'm gonna show you a quick example, and we're gonna go ahead and try to understand how pipelining will make things go faster. Fair enough? So go to Subway, and if you've already been there, you notice that you have different phases when you can check in, stand in line, start the sandwich making process. So they're gonna ask you about the bread, they're gonna ask you about the different things that you need to put in your sandwich, etc. If you want to toast it or not, etc. And then you can get your sandwich ready and check out. For now, so let's divide it into different phases here. I'm gonna call it phases for now, and then we're gonna call it stages. All right, so check in. You're gonna go ahead and choose your bread type and size, whether you want cheese with it in it or not. You want to toast it or not. You want some meat in it, the veggies. If you want to have some sauce or something like that, whether you want it to a combo or just a plain sandwich, or you want to have a drink and chips with it. And then once your sandwich is done, you can check out. All right, so this is one client. One client got in and then got out with the sandwich. Let's imagine that the whole process is taking 7 minutes, right? With the information that is present here, how much time per stage on an average I'll be spending? Well, all I have to do is count the number of stages that I have here and divide it over the time. I mean, it's the other way around, like the time divided over the number of stages, right? So I'm having 7 minutes, and I'm having 1, 2, 3, 4, 5, 6, 7 stages. So basically, I'll be spending 1 minute per stage. Fair enough? Now imagine that instead of having one client, and each client will go ahead and wait for the other, right? So if I want to serve 3 clients, how much time would that take, right? Each client will wait for the other client to finish, to check. You cannot check in. Get it? You cannot start the process before the first client has checked out. So this means that I'm going to spend 7 minutes for the first client, 7 minutes for the second client, and then another 7 minutes for the third client. I'll be spending 3 times 7, so 21 minutes. This is not efficient. I want to go faster. How can I go faster? So let's see. Client number 1 checked in, is choosing bread type and size. Then after 1 minute, I'm moving to the cheese. So I'm gonna go ahead and choose my cheese. So you can notice that the person who's getting, the bread size and type is free now. So another client can check in and go ahead. While the first client is at the cheese level, the second client could be at the bread level and choose the bread. Then a minute later, the cheese client will be at the toast, the bread client will be at the cheese, and then I can check in a third client that will be at the bread level. You can see the pattern here now. So client number 2 will be here. So it's a sliding window, and we can see that we're starting to have some kind of overlapping and some parallelism partially. And then the third client. Now the question is, this is pipelining. The question is, how much time does it take now that I've pipelined the whole process to serve all 3 clients? Well, it's not 7 times 3 equal 21 anymore. It is the original 7 minutes, and every other minute now, every additional minute here, I'm getting 1 client checking out. So this means I'll take the 7 original minutes for the first client, and then an additional minute, so 8 minutes for 2 clients and 9 minutes for 3 clients. And you can see the pattern. So I went from 21 down to 9. Faster, better performance. Right, so this is what I might be giving you at the final exam out of nowhere, and you've never seen before. And we're gonna go ahead and replace the stages of the sandwich making into the stages of the execution. And you already know the classical ones, which are the fetch, decode, execute, that are present on all computers out there. And then you can have some extra steps. Some computers you can have fetch, decode, execute, and write. So here, for instance, you're seeing, instead of the original 3, only the original 3, you're seeing a 4th one, which is the write. And what would the write be, by the way? Take a second to think about it. Write what exactly? Well, it could be the write into the register file, for instance, or it could be write to the memory. It could be anything at all. So here you can imagine, well, it will depend on the ISA and the microarchitecture that you're trying to execute. Alright, so here we're seeing this single cycle implementation, and this means that each instruction will wait. So each instruction will wait for the previous one to finish its execution in order to start the execution. And then here, so the whole data path is a single cycle. So this is the time of all stages. It will define the cycle time. So the whole data path. Unlike the pipeline version here, where you can see that once I started the execution and moved to the very second stage, I can start the execution of the second instruction. And we'll have a sliding window as well. And in this case, the clock cycle will be the time to get into a stage. So we systematically divided it and made it smaller. So this is why we're going faster. Fair enough? Now I want you to think about the stages for the example that we're using in our course, which is the MIPS ISA. So how many stages, according to the implementation that I showed you before, do we have? Is it 3? Is it 4? Is it 6? Is it 20? Think about it. Well, the answer is, I'm fetching for sure, I'm decoding for sure, I'm executing in the ALU, I'm doing something for sure, and then I'm writing back to the register file. But there's still something missing. What is it? Well, dealing with memory, right? So in the MIPS, we have the memory stage. So we have 5 stages in MIPS. Single cycle, we're waiting for the turn. Pipelined, we're gonna overlap. That's the idea. We had a problem. We had a simple implementation, single cycle, simple implementation, which means that it's functional, but it's not performance optimized. Then we went ahead as engineers, created a solution for that, using pipelining. We went faster, and we have a better performance now. Question: with the pipelining paradigm, do we have risks? Do we have some limitations? Could something go wrong? Well, the answer is yes. So usually in engineering, and this is what you're going to face when you're going to go ahead and go job hunting and work in real life. Well, they're going to hire you as engineers to find a solution to a particular problem, to innovate, right? And then you're gonna go ahead and make it work. And then suddenly you're gonna discover that the solution that you implemented, well, it created more problems. And then you need to have with those problems. However, if you can negotiate well, you need to negotiate that you're providing a solution to the existing problem and you're not responsible for the problems that you're creating yourself. You're either gonna hire someone else to solve those problems, and this is what happens in real life, by the way, or you're gonna renegotiate your salary to be able to, solve those problems. This is what we call maintenance, by the way. Right, to make a long story short, here pipelining will solve the single cycle slow performance. I made performance better. However, I surely created some other problems. So what would be the limitations for my pipelining? And by the way, you're gonna go ahead and tackle a study about the single cycle versus the pipeline performance in your tutorials. All right, so let's think about the limitations. And by the way, what made pipelining happen? Well, the fact that everything is easier with the ISA, with the MIPS ISA, that is a risk. So everything is fixed size. So basically, we're gonna read from the same place, and we can have a lot sharing in the data path because we have the fixed size instructions, and then we're gonna go ahead and always in all instructions we're gonna go ahead and get at least one of the source registers in this at the same place. And then the fact that we only deal with memory when it comes to loads and stores instruction and not every single instruction. So you can see that, and of course the memory alignment that we talked a lot about it, so I'm not going to repeat it here. So these factors helped in making the pipelining easier, and we can make it happen in MIPS, for instance. All right, so let's think about the limitations now. Take your time, think about it, and then get the solution. This will give you a good exercise for your future exams and for your professional life later on. So what could be the problems? Think about it from an ISA point of view, from a sequential execution point of view. Like instruction 1 is doing something, instruction 2 is doing something else, and remember we're trying to overlap instruction 1 and instruction 2. So what could be eliminated? What could be something that will bother me when it comes to pipelining, that will make pipelining not possible? Think about it for a second. Alright, so I'm expecting that you find one. Let's do it. Imagine that we're having those two instructions. So adding T1 to T2 and putting, subtracting, doesn't really matter. So I'm using T1, T2 as source registers. I'm putting the result in S1. Then the very next instruction, I'm using S1 as a source register. In addition to S2, I'm putting the result in T0. So here you can notice that there's something in common between those two. So the results that I'm getting here is being used as a source, as one of the operands in my very next instruction. This means that even if I want to go in parallel, go ahead and pipeline, well, I cannot read the value of S1 before this instruction is done, because the value of it will be wrong if I read it before it's done. It will be an old value, and I need the updated value. So here you can notice that I might be able to fetch my instruction for sure, and now that I understood, I can also decode it, doesn't really matter. But now that I understood that I'm using a source register, which is the destination register of the previous instruction, I cannot, continue my execution. I need for my first instruction to finish up and give me the updated value. Fair enough? So this is one problem. Can you think about another problem now? And we here, for instance, we've covered the R-type instructions. So remember the 3 types. So think about another problem, another limitation for pipelining here. What would it be? All right. So what if I'm dealing with the branch conditions? So a branch condition, it can happen, a branch can happen or cannot happen. It depends on the values of the registers that I'm trying to compare, for instance. So if I want to fetch something, in case of a branch, well, I'm kind of weirded out because I don't know whether to fetch the very next sequential instruction or the instruction that I could branch to if the branch is going to happen. So let's see that as an example. So here we have a bunch of things, and then we have a branch here. not equal. So I need to compare those in the ALU, doing what operation, by the way? Correct, a subtraction, using what flag? Correct, the zero flag. So basically, if this is happening, if the branch, if those are not equal and I'm branching, I need to go to the else. So I need to fetch that one. If this is not happening, well, I need to fetch the very next one. Whoops, which one to fetch? So this is a big dilemma. So this is another limitation. And this is what I was expecting from you to find out on your own. I mean, to think about it. And there's a third one. Well, some of the face-to-face people did get it, and this is awesome because I usually ask questions like these in my exams. And then again, you're gonna face something that you've never faced before in your real life, in your professional life. So basically, this is a good exercise for you. So I'm training you. There could be another limitation. Can you think about it for a second? And it's not related to the software, not relating to code. Think about it for a second. It's more related to things that could happen here. Well, a third limitation could be, oh yeah, Patrick, I forgot about Patrick. So a third limitation is about the stages that I could have in my microarchitecture. So basically, what if some stages cannot be separated? So basically, I cannot go ahead and overlap. So it really also depends on the microarchitecture itself and the data path. If the data path is made in a way that will not allow me to overlap instructions, so basically there are no free paths within the data path that I can use when another instruction is using some other path, this won't be possible for me to pipeline. So I cannot divide it into stages that are, could be overlapped. Fair enough. So I'm going to call the first one data hazards. The second one, can you find a name for that? So branching is all about controlling which one will go next. So control hazards. And the final one is inherent to the nature of the structure of the data path itself, or the microarchitecture or implementation. So this is structure hazards, right? I need to focus on those two. Alright, so let's find out. I had the single cycle implementation that is slow. I made it faster using pipelining. By making it faster, I had new problems that I need to deal with. I created new problems. Now I need to find solution for those new problems. So go ahead and try to find a solution for that, a solution for that, and forget about that. I don't care about it for now. So what would be solution here, what would be solution here? So what if instead of using the same register here, I'm gonna go ahead and use another intermediate register, and then later on I'm gonna go ahead and copy the value later. Maybe this could help out. And this is usually what we do. We can do some reassignments, stuff like that. The compiler can deal with that offline. Fair enough? So this is one solution. So I'm gonna go ahead and change the instructions, the order of the instruction in a way that does not affect the execution of my program. So this is all about how the compiler deals with that. So reordering the instructions. What else can I do here? Let's try to analyze it as engineers. Give me a pen. So let's see what I'm doing here. I'm getting something from the instruction memory, going to the what is the next thing that I'm doing here? To the register file, going where next? It's a sub. So I'm gonna go to the ALU. Am I using the memory? No, I'm not using the memory. And then I'm gonna go ahead and write back to my register file. Can I go faster? Let me rephrase that. Can I get the information that I need in a faster way, instead of waiting for my instruction to write back to the destination register here? Where can I read it? Well, you can notice that once I'm done with the ALU, well, the result is ready. All I'm doing is waiting for it to go ahead and go back to the register file. So maybe I can shortcut the reading of my instruction here, of my value here, and use it in the next instruction. This could help me go faster. Fair enough? This is what we call bypassing. So instead of waiting for it to get back to the register file, I'm gonna go ahead and read it on the road, or no, on the route, not the road. Fair enough. So maybe I can use some additional wire here and go ahead and get it from here. And this is bypassing, or also known as forwarding, to forward. Don't worry, we're gonna cover those in details later on. But I'm just trying to make you think about those and use your engineering skills. This is a solution for that. Find me a solution for that. Go ahead, analyze it, and think about it. So to think about it, let's see. I have a bad situation. Any improvement of that bad situation will be improvement. So any improvement that would make me go faster, I should take it. Let's see. What are the chances for me to go here? Statistically, probabilistically and statistically point of view. That's it. What are the chances for me to go here? It's 1/2. It's a 50% chance for me to execute the very next sequential execution here, instruction here. What are the chances for me to execute that one as the next instruction? Well, it's 50%. So it's a 50-50 chance for me to go here or go here. So what should I do? So instead of waiting, I could just stall. Get it? So I can just wait and maybe execute other instructions that are not affected by that, and then go back to that. This is an easy solution, right? But again, there could be some waiting, because sometimes other instructions cannot be executed because they will be affected by that, or there are no other instructions to execute. So waiting is a possibility, but I want to try and go faster. So in order to go faster, what can I do is, what I can do is go ahead and assume that the branch will always happen, or the branch will never happen. This is an assumption. So I'm going to say that whenever I run across a branch, I'm going to go ahead and load the very next instruction, or the instruction that I should load. One of the two. It doesn't really matter. So let's stick to the branch happening. So I have a 50% chance, if I have a branch, to take it. So I'm going to go ahead and fetch, decode, and execute. So I'm going to load my branch instruction here, my branch 2 instruction. Fair enough? The one that I'm branching to. If worst case scenario, well, I've loaded it, so I fetched it, etc., etc., and then I realized that I made a mistake. Well, I'm gonna go ahead and empty it. This is the worst case scenario. Best case scenario, however, the best case scenario in this case is I've already loaded it, and I'm indeed branching to it, so I went faster, as if the pipelining is normally happening. So it's a 50-50 chance for me to go faster. So if it happens, good for me. I'm already fetching it. If it didn't happen, well, this is where I have some kind of penalty to pay. And statistically speaking, it's a 50-50 chance, so I'll take the odds. It's better than nothing. Fair enough? So these are the things that I explained to you in the previous slide, and that's it for today's video. And I really hope to see you face to face sometimes. It will be nice for those who I've never seen face to face, because I've just seen like 100 or so students out of the 500, so it will be nice to see the others as well.